What I'm just going to do is tell a little bit about what the AECB has been up to fairly quickly, and then describe a bit about where our head is at. You know, how are we thinking about things? Right, so a little bit about the membership. We seem to be seeing an increase, which is good. 25% increase in members over this year. We have members from every sort of corner of the industry, and many of those members are people who have been pioneering for years and deploying and leading on best practice. So it's a very well-rounded membership. Building standards, I'm sure you're familiar with. There's the new build standard, self-certification, 2 retrofit standards now. We've got the original one, which we're calling level 2. We've got a new one, which is a heat pump-based light retrofit standard, which I'll just touch on, which we've been doing a lot of sort of research into to make sure it's a viable standard. We have a water standard, as you know, and then the lifetime carbon standard and the daylight standard are not actually certifiable standards as such. So we're going to be developing training to help people understand and deploy all of these standards. So this new level 1 retrofit standard is based on the fact that we do recognise, so we've challenged ourselves on the deep retrofit agenda. Deep retrofit is a very meaningful, useful thing to be doing, but it's not the only thing we should be doing. So we clearly need to get off fossil fuels rapidly. Heating by electric heat pumps offers an easy and potentially cheap route when combined with relatively light fabric retrofit. So it's not an intrusive approach, which a deeper retrofit obviously is, and that's what we're struggling with. We do require good ventilation to be installed as part of that, and obviously we have an eye on the running costs after the retrofit, so we're trying to pay a lot of attention to the reality of the performance gap and make sure that after such a level 1 retrofit, heating costs are not higher than the fossil fuel system you've come off, so we're doing some economic modelling on that. We're not discounting going on to level 2, so level 1 is either a step towards a deeper retrofit, level 2, or those buildings at level 1 may well be sitting there operating on that level for years, 10, 20 years. And so we've been looking at what happens if we have 2 waves of retrofit, a level 1 and a level 2 over time, and you'll illustrate this in a minute. Is that still a meaningful thing to do? Because one of the things we've been worried about in the past is people doing shallow retrofits which lock out future improvements. So the standard we've developed is designed to not block that second, deeper retrofit. So it's thinking ahead on a long-term plan. So just to give you it's a overly complicated graph, but what it shows is the existing housing stock. And obviously what we need to do is to get that entire housing stock and shift it over here to reduce the space heat demand. So when you're thinking about reducing the need for heating, we have aspirational standards like Enefit, which will apply to a relatively small number of homes perhaps. I live in one, and it's very, very comfortable and very low energy. Very happy I did that. The level 2 retrofit standard is less demanding, but still a meaningfully and useful standard here, which we set at 50. Now, there are exemptions within the AECB level 2 for listed buildings or other very good reasons which we set out. So potentially, a certified level 2 retrofit could be demanding 100 kilowatt hours per square metre. So it's actually a range. Now, I've put a note here that space heat demand is not the same as delivered heating energy, which is what you pay your bills on. So with the level 1 retrofit, there isn't a space heat demand target. What we're doing is making sure that there are just enough retrofit measures and ventilation measures to ensure a relatively healthy building, but we're using a well-installed heat pump system. We're using the efficiency, the very impressive efficiency of heat pumps to, in effect, reduce the heat demand through 350% well-installed heating systems. So this is the criteria by which you would certify to a level 1 retrofit. So I've just picked out the sort of key features here. What we're doing is changing the heating system from a fossil fuel system or direct electric heating to a heat pump. We're thinking about forward planning, so we need a long-term energy plan, and that currently is using PHPP. The heat pump system, we're looking for that efficient installation. So we're talking about the relationship of the heat pump with the radiator, the heat emitters, the underfloor heating, or the radiator sizes. And if we can get that right, and what we thought is the best criteria is actually setting the flow temperature for the heat pump designer to actually be low enough to get those efficiencies that we need to keep the running costs under control. So that's one of the criteria, flow temperatures less than 45 degrees. Controls is an important area we're still doing work in, but that probably will turn into some sort of criteria. And air tightness, feedback from members about what is possible whilst not going deep into a building. What can you do from outside? You know, if your existing homes are around about, well, I mean, they could be already our target. Existing homes could be at 5, but typically they might be at 6, 7, 8, 9, 10, even 13 or more. So this is an important criteria, and we've set it at 5, whereas the level 2 retrofit is 2, passive house new build is 0.6, and NFIT is 1. So it seems like a doable and reasonable target, still stretching, and this is permeability. We must have ventilation, so we're putting in sort of optional requirement to show that you've put in adequate ventilation to maintain good air quality, and of course there's an overheating criteria. So here are the 3 typical house types we've used, and then we've chosen the cavity walled semi-detached house as the kind of easiest one that is most typical of housing across the UK. So it's actually a very useful house type to try to illustrate what a level 1 standard might look like. So for example, we talked about air tightness, so the semi-detached house you'd aim to get down below 5. We assume 50 mil of cavity wall insulation in place. If it's not in place, then it would have to be put in place. So there is a fabric measure there, but we're assuming this is a starting point, that there'll be some relatively poor cavity wall insulation in place, that there'll be some double glazed UPVC plastic windows. Again, if they're single glazed windows, not many houses now have those, but that would also be another measure you would need to employ for level 1. And then basically on goes the heat pump. So that's a sort of package. Oh, with a topping up attic insulation to around 400 millimeters, so that might require some attic top up. So you can see it's a potentially a lightweight, sort of light retrofit. So we're not insulating floors there. And so the sort of key things we're looking for from the people who model using PHPP, you will get an increase in internal temperature, average internal temperature. You will be looking to make sure that the running costs, the electricity running costs, are no more than the gas or oil that you've come off, so you need to keep your eye on that. And of course, we're looking at this very significant reduction in greenhouse gas emissions because you're going off gas onto electricity, the national grid is decarbonising, and these issues that we have been fretting about, how much electricity is going to be available to shunt 80% of homes from gas to electricity. Can the grid cope with that? Well, it won't be able to cope with that without increasing the capacity. But at the moment, for the next 5, 10 years, we can get on with this. So there is an issue of peak heat demand, but we're not letting it get in the way of proposing we get on with this type of retrofit. We have to focus as well on resource efficiency. So we end up with this sort of list of basic principles. If we don't need to build, or we can find another way to satisfy the client's brief that actually doesn't involve building, don't build. That's a very sensible approach. If we do have to build, look for opportunities to retrofit first to satisfy the brief. If we do build or retrofit, don't make it too big. You know, that's sufficiency, modesty. That's quite hard to sell to clients, but we do have to be thinking about that. Obvious things like making it adaptable, make the individual components last a long time. We don't want, if we're using a lot of timber components, we don't want that coming back into the atmosphere sooner. It's later rather than sooner. I really want to encourage all of you who are not working to the AECB standards to actually just start working to the AECB standards and get them certified. It really gives a clarity, whether it's a passive house, NFIT, AECB new build, or the 2 retrofit standards. Working to a standard and self-certifying it on the system gives a real clarity. It also helps with clients. Once the client has agreed to work to a standard, it gives you a much stronger hand when they're making changes, last-minute changes. It's basically, no, it's falling out of the standard.
In the last few years, having, I suppose, increasing confidence that as an industry we understand now how to crack the operational energy issue in new build and in retrofit and to quantify that accurately. We've moved on to embodied carbon. We're talking in terms of CO2 equivalent, which is of course the carbon dioxide and other greenhouse gases converted into an equivalent amount of climate kind of damage, essentially. One of the key things we need to look for, and these are really the building blocks for a life cycle assessment, are environmental product declarations. Now, they're not available for every material yet, but rather than just having a cert claiming that a product is green, what we have with an EPD is a standardized, independently verified audit of a product's overall environmental impacts. They're very challenging to obtain, depending on how complex the product is, I suppose. And they give you things now in a standardized way. They give you values such as the kilograms of CO2 equivalent per square meter, that would be the functional unit, for instance, or per watt peak in the case of a solar PV array or whatever it may be. And there's increasingly stringent rules being laid down now, product characteristic rules, to enable you to fairly and consistently compare materials. So that's, I suppose, really important. There's been a really weird transition happening. I've noticed it in Ireland in particular, and it will be happening in the UK too. I've had conversations with either directly with developers or with suppliers for big developers who all of a sudden are starting to move on life cycle assessment, on looking for environmental product declarations for products. But it is amazing to see among developers in Ireland how quickly this is changing. I know companies who are under pressure from developers, heat pump suppliers, building fabric product suppliers of different kinds, who are under pressure to get EPDs just to be able to be involved in a project in the first place. A few key documents, I mean, you can have the slides afterwards. RICS, their methodology has been really, really important. It's worth reading that. It's a big document, but it's worth reading. That's meant to be being updated, but that's been paused for now, I gather. The scope is really, really important. So we were used to seeing at a stage architects coming forward with building LCAs where they present a mass timber building, for instance, and they'll just show you an embodied carbon score for the superstructure, and claim that it's a carbon negative building. You can't get away with that. The RICS document defines what the scope must include and then what's possible to include within it. REBA, with their 2030 climate challenge, define what they require people to submit, and it's basically everything in this list, which goes through from facilitating works through to finishes, excluding external works and also demolition at the start of the project. There's assumptions in the RICS document about lifespan. The assumed reference study period is 60 years for different building types. Now, we have to hope that the buildings that we're designing now will last a lot longer than that. There is some data for non-domestic buildings in particular to show that the lifespan can be much shorter, often not because there's a problem with the building, construction quality-wise, but because of growth and densification requirements and so on. But that, we have to assume, will have to change in the kind of post-apocalyptic future that we're heading into. Just to explain how this works in the context of building life cycle assessment. So the conception and gestation stage, this is the emissions involved in manufacturing the products, in transporting them to site, and in the construction and installation process. At this stage, we can have high confidence about the emissions because it's possible, especially if you've got EPDs, to get really good quality data on how much emissions have actually been released into the atmosphere, and also how much are stored in, how much biogenic carbon is stored in components in the case of timber and timber-based kind of products. When you get into the life stage, which deals with emissions released or sequestered by materials during use, there's a kind of a funny one here with concrete-based products. There's a process called carbonation, many of you be familiar with. A lot of carbonation can be very problematic for concrete. If it's structural concrete, it can cause the concrete to fail, so you have to be careful about it. It can cause corrosion of rebar, for instance. But it's acceptable in certain uses. But you can get a fair amount, depending on the concrete product, you can actually get a fair amount of sequestration, depending on how dense it is. If it's very dense, for instance, and if it's buried in a wall and not exposed, you don't get as much. But I'm a bit wary of this because it can happen over long time spans, and the cement industry is inclined to kind of try and claim probably more than it's really entitled to. B2 and B5 is maintenance, repair, replacement, and refurbishment. I should say B6 and B7, operational energy and water use. They're excluded in the likes of the REBA standard from their embodied carbon totals. They report on them separately. When you get into B, you start making big assumptions. How long will a component last? And how polluting will the manufacture of replacement components be? Well, we don't know. It's important to look at it, and it's important to think about the quality of components and the quality of the work from a detailing perspective, the installation process and so on, to try and ensure that you get a longer lifespan. Then in the death stage of the building, you've got deconstruction and demolition, transporting away materials, you've got waste processing for reuse, recovery or recycling, and then you've got disposal. More big assumptions are being made here. How long will the building last? how polluting will the disposal be. Timber suffers in this stage, actually, the way it's treated in the life cycle assessment methods, because you get all the benefit in the gestation stage of the stored CO2 from when the trees were growing. And of course, that isn't a license for just clear felling. You know, there's nuance in all of this. But whatever you do with the timber, whether it's incinerated, landfilled, or recycled at the end, it's assumed to be released into the atmosphere, or rather it moves beyond the boundary conditions of the life cycle assessment if it's recovered. So the sequestration passes on to the next use. Which now, what I mean by grave robbing is this kind of nightmarish concept of taking body parts and making a new entity out of it in the future, you know, a new building, which is great, of course. It's Frankenstein monsters is I guess what we need in the future. But those benefits are not considered within the targets that we're looking at. So that's just how I would divide those tables up. That's my own twisted way of thinking anyway. Look, get calculating so we can have these discussions. Pick apart calculations, you know, that other people are doing. Peer review is really important with this too. There's lots of tools available. One-click LCA have a good tool too, but my own preference from what I've seen will be pH Ribbon because it's Excel-based. You can reverse engineer the calculations and really kind of pick them to pieces. And if you've got a building put into PHPP already, it really speeds up the whole process because you've got a lot of the heavy lifting already done in terms of the areas and stuff added. EPDs really matter. Try and get them wherever you can. There's some areas where they're available, some where they're not. We've just seen a first EPD published, to my knowledge, globally for a heat recovery ventilation system, for instance. And they'll be slow coming for things like heat pumps, but they are coming. Query the assumptions made after Module A, after the gestation stage. If a building is someone's offspring, we don't know what they're going to do in the world. And I know it's morbid sort of talking about the death of something that you're trying to create effectively, but we do need to grapple with that. And I think there is an argument for placing more emphasis on in the way that Letty have done, on Module A targets. Thinking about the full cradle to grave, but I think Module A's, you know, the gestation stage stuff is the stuff that we can have most confidence about. And that's the stuff that we're putting into the environment now. So I think that's where a lot of our emphasis should lie, really. Thank you anyway for listening.
So Enmite was founded to help resolve a long-standing need for work-ready engineers.
We'll be leading a tour along with the site manager, Sophie. We have an absolutely fabulous building to go and visit.
We have used no coverboarding at all on the project, so all of the timber that you can see is structural, and we were erecting through winter, which, as you can imagine, was painful and stressful.
The workshop sessions here with the individual experts.
Whether we're changing the architecture or we're just making changes in order to retrofit, how those changes influence how that structure behaves.
On the one hand, advising people they need to be using low embodied carbon materials, and then in the case of cavity walls, then telling them that probably the best solution is to put polystyrene bead in, and realising it's not a nice material.
I used to get laughed at because I was saying we should build houses out of straw. Now we've got the prefabricated panels, which are a game changer.
Kind of a selfish aspect to this as well. It's much nicer working with natural materials. And the couple of projects that I've worked on with Andy in the last couple of years have resulted in the assembly that we'll be looking at later.
The wall system that we worked through with Andy Simmons and with Tim Hulse was a novel approach to airtightness. So instead of a traditional two-membrane approach, the airtightness membrane is on the outside. So it required a building physics approach, some assessment and some analysis of the existing buildings. So we had an existing structure, which is a cavity wall build, and we wanted to assess and try to get an idea of what the airtightness was initially. And to find out at what point the airtightness would need to be improved to make this system work. So we assessed it and stressed it using WUFI, and we found that 5 air changes was a safe figure. So if you can bring the existing building to 5, essentially this system, be it a 200 mil I-beam or a 250 or 300, will work. So really what we're talking about is cellulose insulation under pressure. We've got this membrane here, which is a breathable racking board, if you like, as well. So that's vapor open, this is vapor open, so it always has the ability to dry to the exterior. In addition, I guess we've got some structural insulation used around windows and doors, that's the Almavert. Overall, the general idea is to have a super simple structure, a very simple idea. This is uncomplicated, it's readily available everywhere. Cellulose is the same with the membranes, and the skills needed to do it are readily available. What we found really interesting was we installed some monitoring so we could check and validate that what actually happened over the 2 years post-install matched what we had analysed on WUFI. So a really solid outcome, and I feel like a validation that the system works as planned.
What we're focusing on at the AECB conference this year is partial retrofit, because it's acknowledging that homeowners can't particularly do everything all at once, so it might be a staged process. So our model is focusing on suspended timber floors. As we all know, as we're sitting down in our little cottages or whatever, that's where the draft comes from, is under our feet. So eliminating that through a very strong system which absolutely encourages moisture management and a natural insulation system is key.
So the whole basis of this system is that you have a wind-tight breather membrane. So this is called Proclima Solitex Plus. It's moisture vapor open, and I always say that it's like a Gore-Tex jacket. So in other words, you don't sweat, but it's also wind-tight. It's a monolithic membrane. So it's stopping any air coming through, but it's allowing any moisture vapor to harmlessly diffuse out so you don't get any moisture buildup. And then this top membrane is your airtight vapor control membrane. It's kind of retarding any moisture vapor transferring from inside to outside by diffusion. So you're not getting any buildup of condensation here.
Styco are a manufacturer of wood fibre insulation materials and I-joist structural timber products. We're promoting a system based on internal wall insulation with a wood fibre, and it's based on internally insulating existing masonry buildings, so existing solid masonry structures, of which there are millions in the UK that need insulating. Now, where people have traditionally been insulating existing solid walls, they've been using an insulated plasterboard approach. So it's typically plasterboard bonded to a PIR or an EPS type insulation and a dot and dab process on the wall. What we've come to sort of see over time with people using that system is when you're installing that, you're creating a cavity between the existing wall and the insulation layer. Any warm air that gets through the insulating layer, hits the cold air surface, will condense and you'll produce liquid water. That liquid water will run down in the cavity and it will produce mold and damp problems. And that is occurring in a lot of buildings. I think there's so many ways you can overcomplicate, particularly retrofit situations, and it can become very difficult, very complicated, very expensive. And actually, if you've got a building that's relatively difficult to deal with, a thin layer of internal insulation is actually the easiest way and the cheapest way to go forward. What we do with a natural insulation is that we bond the wood fibre board to the existing wall. So we have got between the existing wall and the insulation around about 8 to 10 mil of, depending on what insulation manufacturer you're using or what lime or clay system you're using, a bonding coat between the two. That bonding coat is an integral part of the system because it ensures there's no air gaps between the insulation and the existing wall. So it's impossible for liquid water to form and run down the cold wall surface. Any moisture or condensation that gets created, because you're using a wood fibre approach, is stored within the fabric of the insulation itself. The product can hold around about 20% of moisture by volume, and it can naturally allow it to evaporate either to the outside or back to the inside. It's what is traditionally talked of as a breathable wall solution, which in turn ensures that the internal environment has low humidity, so it's a healthy internal air climate.
So, welcome everybody. I'm here to tell you about the EcoCocon straw panels. It's a very, very simple panel. It is exactly what you can see. It's 4 pieces of timber at the corners of the panel, timber at the top and at the bottom, and then plywood. And it's screwed together with screws with big heads on. That's it. It's 98% natural timber and straw, most of it straw. timber's all FSC certified. The straw is tested for pesticides and fertilisers before it's used, and there are never any residues. And the straw is compressed to a density of 110 kilograms per cubic metre, which is the same density that we get in a normal load-bearing straw house. And at that density, you can hear that's the thud of a dense straw. At that density, then you get the optimum insulation value and you get the best fire protection. So there is not enough air in here to burn, and all the fire tests prove it. And there is enough air to give good insulation. So you've got the combination of fire protection and really good insulation. And insulation does more than one thing. It doesn't just give you a U value. And that's the message we're trying to get out with all of the natural insulations, is it's also a breathable system. So the natural fibres deal with moisture. You don't get interstitial condensation in these panels. It just does not happen. And the way that you put them together, the panels can be anything from 400 mil wide to 1.2 metres wide, and they can be anything from 400 mil high to 3 metres. But obviously you want to go more than 3 metres to build something taller, and we just put them on top of each other. They're just like giant building blocks. You've all done it as kids. You just put them together and you can get millimetre accuracy. So it's all about, it's modular building systems. It's all about planning and logistics and getting that right. So it all comes on a big articulated truck and you offload it according to how you want to build the system. So on the inside, we would recommend using a wet clay plaster. On the outside, if you're wanting to achieve passive house, then you'll need to use a membrane. So the outside skin is the airtight layer. So when you build them each day, you put your membrane around, which also gives you weather protection. You cover over your windows and doors, and you fasten the membrane on with 5 mil plywood pieces which cover, so that in themselves is another protection for airtightness, which covers the joins between the timbers. These are all supplied as part of the package. And then onto that you put, if you want to achieve the passive house standard, 60 millimetres of wood fibre board. So this is a certified product. It will already go through the passive house system if you follow these details.
We've had a really good day at the AECB conference, so really good attendance, engaged people, and I suppose very ecologically minded but practical as well.
AECB is a group that is committed to basically have an impact on reducing both carbon, energy and the change that is needed in the UK.
If we want to upskill and reskill our future workforce, we need to work with the industry, we need to work with future and current professionals, and we also need to work with academia. So to me it seemed a natural role to bring everybody together, which is what I love doing.
Well, coming to the conference is a must. It's rare, especially over the last few years, to have so many people together, come together and share knowledge.